So in the last lecture, we discussed about phase transitions for one component system, meaning we only discussed about pure substances. So in this lecture, we'll discuss about mixtures, which means what happens or how the thermodynamic properties change if we add two substances or more substances together. Now, we'll first give you a very simple example. Suppose we have two liquids which are immiscible. Now, if we have, say, for example, water and oil, and if you add water and oil together, the change in volume, if you add, say, 10 ml of water in 10 ml of oil, or the other way, since water and oil are immiscible, so the total volume will be nearly 20 ml. So you can approximate that the volume, total volume is V1 plus V2 or V water plus V oil. However, if the two liquids are miscible, meaning they form at the molecular level, molecule of one liquid form a bonding or some interaction with the other liquid, then the total volume actually is not just simply additive of the two volumes. Now we can give an quick example. Suppose you take ethanol and water, and ethanol and water if you mix, now ethanol molecules actually form hydrogen bonding with water, and so there is a strong interaction, and you will not see the volume changing as an addition of the two liquid or the addition of volumes of the two liquids. Now we'll first show you some experimental data. So here what we show is how basically if we add ethanol and water together, how the volume changes. Now remember that the volume we are talking about is a quantity which is known as a partial molar volume, which means how the molar volume changes if we keep on adding one particular component. In this curve, we started from 0 mole fraction of ethanol, meaning we started from pure water and we kept on adding ethanol. So 0.2 means this mixture will be 0.8 mole fraction of water and 0.2 mole fraction of ethanol. In this way, we show up to 1.0 mole fraction of ethanol, which means it is pure ethanol, where water content is 0. Now think about it. When you start from pure water, or the mole fraction of ethanol is 0, at that point the molar volume will be nothing but the molar volume of water itself. Now molar volume of water you can easily calculate. Remember, we are denoting the molar volume as V suffix m, and that you can easily calculate. Water at normal pressure and temperature has density of 1 gram per cc. So 1 cc is nothing but 1000 liter, or 1 liter is 1000 cc. So we can just write 1 by 1000 liter. So in that way you can ask 1 gram or how much weight 1 liter water has. So 1 liter water, it means actually 1000 cc water, or the weight will be 1000 gram because the density is 1000 gram per cc. So it will be nothing but 1000 gram divided by the molar mass of water, which is 55 if you take H2O18, or sorry, O16. So I have to divide by 18, and then the molar mass will be 18 gram per mole. So the molar volume is nothing but you can easily calculate it. It will be 55.55 mole. So if you take this to be O16 isotope. So you see here that the molar volume which we got here will be 18 gram per mole, and that's where it starts. This is basically the density of the liquid. So in this plot, we show how the mole fraction of ethanol, if we keep on changing that, how the partial molar volume of water or ethanol changes. Now by partial molar volume, we mean that the change in molar volume per unit addition of one component. In this case, we are varying only ethanol. Now think about it. Here we start from 0 ethanol, which means initially it was pure water. Then we slowly keep on adding more and more ethanol, which means at this point, 0.2 means it is 0.2 mole fraction of ethanol, which automatically means it will be 0.8 mole fraction of water. And then ultimately we go to pure ethanol, where the mole fraction of ethanol is 1, which means that the mole fraction of water at this point will be 0. Now you see here that the molar volume of water, so in units of centimeter cube per mole, it is nothing but the 18, it should be 18 because the molar mass of water is 18, and then ethanol, it is 58. So you start from 18 here when it is pure water, and then it drops directly to 0 when it is pure ethanol. And ethanol similarly starts from nearly 0, and then so the 0 point is not shown here because there will be a sharp rise and then dip, and then you get the pure for pure ethanol, it is 58. Now the interesting point here is that if you add these two points, the addition of molar volumes, it never follows the total volume. So that means it is possible because H2O, water, and ethanol, which is CH3CH2OH, they are actually miscible. So the volume is not simply addition of the two volumes. Now in order to quantify that, this quantity, partial molar volume, we define it as the partial molar volume of any component, which we denote as I. So I is a component. So in the previous example, the components were ethanol and water. So it's a two-component system. Any arbitrary component I. We ask how the volume is changing if we keep adding the component I, or if we change the number of moles of the component I at constant pressure, temperature, and of course all other components which I denote as, say, Nj, where J is not equal to I, which means we have to keep all the other components constant. That meaning is if we are adding ethanol, so we cannot add water simultaneously. We are only seeing how addition of the ethanol is changing how the volume is changing by addition of ethanol, when the volume or the addition of water is not done. So you can either could have changed you could have either added water, then the curve will look like this, the curve for water, from 0 for water concentration mole fraction to maximum 1, or you could also do it by adding ethanol. Now interestingly, remember that if you just ask me that what will be the total differential of changing the volume, so that differential at constant pressure and temperature should be the partial differential when we change the component A. Suppose I can be here A and B, so it's a two component system. the example we gave, A was water, B was ethanol, something like that. And then we take the change in A plus the partial derivative when we change, it should be V, the change in volume, the partial derivative with respect to NB, and then multiplied by dNB. But when we change Na, which is the number of moles of A, if we keep on adding, we have to keep in mind that we are keeping pressure constant, temperature constant, as well as NB constant. Similarly here, we are keeping pressure constant, temperature constant, and Na to be constant. So we can integrate it and ask this question. Before integrating, we can just write it in a shorthand notation. We could write it as Va dNA plus Vb dNb. So where Va and Vb are the partial molar volume with respect to A and B respectively. So partial molar volume is defined as, partial molar volume of a particular component is defined as how the total volume is changing but if we add the particular constituent or component. So we can ask this question, what will be the total volume? So that, or the total change in volume due to this addition, that will be simply integration of this change, and we can easily find out the quantity. So it is nothing but the Va dNA plus integral of Vb dNb, and if we assume that this quantity V and Vb is not changing over the entire range of change, which is an approximation of course, because we showed that the curves are not very linear, the curves are very much nonlinear in nature. But still we are assuming that V and Vb are constant when we add, when we change the Na and Nb. So then with some approximation we can write, actually it is Vna plus Va Na plus Vb Nb. Now the question is how the curve will look like if we add some, change some volume, something like that. So you see that a general nature of the curve is very nonlinear, in the sense that if we plot the V versus a mole fraction of A, the slope of the curve is nothing but the partial molar volume, because remember, by definition this is the slope, so dVA dNA or del VA del V del NA, that slope is actually changing. So this approximation which we made that during this change Va is constant is not a correct approximation. So all we are saying that within a small range, maybe we can assume that this slope does not change. Now the next question we ask, since we are doing all these experiments at constant pressure and temperature, now the question we are asking is that what happens to the Gibbs free energy? Because Gibbs free energy is a natural choice to look at, and from there we can actually calculate what are the conditions that these two liquids will spontaneously mix or not. Now for that, in a similar way, instead of Gibbs free energy, we use the definition of chemical potential, which we already discussed, but this quantity we call as partial molar Gibbs free energy. The reason partial is coming because we are now talking about mixtures, so we cannot say it's just molar Gibbs free energy or something like chemical potential. So it's a chemical potential of a particular component in the mixture, because there are multiple components, at least there are two components, that's why it is a mixture. So in a similar way, just like we defined the partial molar volume, we can say that this quantity will be nothing but change in the Gibbs free energy per unit mole of addition of the component I when all other components are kept fixed. So J not equal to I. So we know that we already know this equation. G is mu A, or we can actually start from this equation first. The dg will be nothing but mu. Suppose we have two components, and then if you ask this question, what will be the finite change in the dg? So you can easily, in the same way, just like we did the partial molar volume, if you remember that we showed it as VA dNA plus VB dNB. In the same way, we can write it as mu A dNA plus mu B dNB, where mu A and mu B are partial molar free energy. In the sense it is partial, that we are writing it for two component system where the components are again A and B, and that's why it is partial, and it is molar because it is per mole. So Gibbs free energy per mole is nothing but the chemical potential. That's why directly writing mu A here. So this is nothing but the finite change or the differential change in this context, and we call it as a partial molar free energy. And in the similar way, we can write that if we integrate it, we'll get the Gibbs free energy, which we wrote can write as, say, mu A Na plus mu B Nb. Now, interesting thing to note here is that we already know expression for dg, and the expression was, if you remember, so remember that this dg is at constant pressure temperature, that we should always keep in mind. So just like here also, we should always write that it is at constant pressure temperature. Now the general equation for dg, if you remember, that we wrote dg as minus sdt plus vdp. Now if we make the condition at constant temperature and pressure, this was for one component system. Now for multiple component system, we see that there is a contribution of dg when the pressure and temperature is constant. So when the pressure and temperature is constant, from this equation dg should be 0. But now we are seeing that there is an additional component of Gibbs free energy, which is coming from the Gibbs free energy due to mixing. So we call it as a Gibbs free energy of mixing. And so the total change in the Gibbs free energy, if we vary temperature, pressure, as well as all these quantities, can be written as minus sdt plus vdp plus all these quantities mu A dNA plus mu B dNb, which we can write as a general equation, that it will be a sum over all these terms which involve mu I dNi. So this is a much more general equation where it not only contains the information how the Gibbs free energy is changing with respect to temperature or pressure, it also contains information if we keep on changing the fraction or mole fraction of one particular component, how the total Gibbs free energy is changing. Now remember that we also discussed that dg can be equated to the maximum additional work. By additional work, we meant that it is a non-PV work. For example, some electrical work in when electrons flow in a circuit, so it also does some electricity to flow, and it does some work, because electron running through a potential difference will there will be a kinetic energy involved, and there will be some work done. So that work is a non-PV work, non-pressure volume work. So those kind of work we talked about, and we said that it's additional work, and we asked you to show it because for if you remember that we derived the other equation, which is basically the Helmholtz free energy is equivalent to the maximum, we should write d cross here, PV work or maximum work from the system. Similarly, for the Gibbs free energy, we found that we did not derive it in the lecture. We asked you to derive that the Gibbs free energy change is equivalent to the maximum non-PV work or the additional work. Now that means that we can actually have a physical meaning of what is the change in Gibbs free energy or what is the change in Helmholtz free energy. It can be directly equated to the work done. For Helmholtz free energy, it was the pressure volume work done. For Gibbs free energy is the non-pressure volume work done. Now, if we write it in this way, so we can easily see the meaning of this maximum additional work, and this additional work is nothing but we can write it as d cross w maximum additional work. This is nothing but the mu I dni, because remember that this part will involve the, if you work it out, you will realize that this part will be equivalent to the work done, which is relevant to the PV work. So when we solved it, we said that you take the d cross w as d cross w PV work, which is P opposing plus dV, and plus write it some additional work, and then you can show the additional work will be equivalent to some non-PV work, which is this term, and then we can easily show that d cross w maximum additional will be the change associated by changing the components of the mixture. So what we see here is that when we make a change or make a transformation, so then there will be some PV work, or there will be some non-PV work also. In this case, if you simply mix two liquids of say two fixed volumes, what we are seeing is that the volume change is not just simply additive of the volume, there is a change in volume, and we defined the partial molar volume for that, and we saw that the curves are not just addition because there is a miscibility between the liquids, and additionally we can also define some change in free energy associated due to the mixing. We'll also quantify it. We are right now just writing it as a phenomenologically, just saying that okay, we are assuming that there is a change in free energy, and that will be equivalent to mu I dni. But that change now, since there is no change in the pressure volume kind of work, so we are saying that this is a non-pressure volume work. It is just happening due to the mixing of the two liquids, and that is nothing but the summation of chemical potential of each term multiplied by the change in moles of that particular component. And if we take the sum, that will be equivalent to the maximum additional work, which is the non-PV work. Now let us move on, and this partial molar free energy, which we defined as say G del N I. So now mu I, as we told, it's known as a chemical potential of that particular component, because it's not just mu. In the when we are discussing the phase diagram or the phase transition for one component system, which is a pure substance, say for example water or carbon dioxide, there also we talked about mu versus T curve and so on. That mu was just the chemical potential of a pure substance, and mu suffix I is the chemical potential of that particular substance. So let us now try to understand this chemical potential. Can it be written not only in terms of the Gibbs free energy, but also in terms of some other thermodynamic parameters, for example say internal energy or enthalpy or Helmholtz free energy. Now you can easily figure that out, because we defined already chemical potential in terms of Gibbs free energy. Now Gibbs free energy is nothing but H minus Ts and H is nothing but U plus PV minus TS. So we can right away see that du will be nothing but, if I just take this PV minus TA term on the other side, so it will be minus d of PV, so which will be we can just keep it like that for the timing, plus d of TS, and then you can show that this will be again nothing but if we just keep the H constant. So now for dg you can write minus SDT plus VDP plus all these sum over mu I dni terms, because we are considering mixing right now, and then you can figure out all the other terms will cancel out, because it will be nothing but minus if we take the pressure derivative first, minus VdP, then it will be minus PdV, plus we have TdS plus SDT. So this SDT cancels out and VdP cancels out. So du will be nothing but, if we write it in this way, the way we are writing it, TdS minus PdV plus, now we have a term which is mu I dni. So you can see here that just like we wrote dg as the SDT minus SDT plus VdP plus sum over mu I dni, similarly the du equation is also modified as TdS minus PdV plus sum over mu I dni. So this mu I can be expressed not only in terms of dg but also in terms of other quantities. Now remember that we started with this, that mu I is nothing but taking the partial derivative of Gibbs free energy as we change the component I, keeping pressure, temperature constant and all other component constant. Similarly, if you look at this equation, we can take the partial derivative with respect to Ni, keeping this time I have to keep entropy and volume constant. I can keep entropy and volume constant plus all the component which are not I except that particular component. So we are changing only that component. Similarly, we could also write it following the same logic, a partial derivative with respect to enthalpy, and remember the enthalpy equation, it was TdS minus VdP. So we have to keep entropy and pressure constant for H, and similarly we could also write it in terms of the Helmholtz free energy, del A del Ni, and for Helmholtz free energy remember that it was PdV minus and TdS and PdV, so SDT and PdV. So basically the natural choice for Helmholtz free energy was to keep the volume and temperature constant and Ni not equal to Nj. So mu can be expressed in any of these thermodynamic quantities, either G or U or H or A, whichever you wish. Usually we use this definition because the transformations are happening at constant pressure and temperature in most of the cases, but you might have a situation where you have to use the Helmholtz free energy where the volume and the temperature are kept constant. But in other cases you could also use U or H, but those are rare because usually we are not considering, or we are not giving example of a process where entropy and volume are kept constant or entropy and pressure are kept constant. Now, so what we discussed so far is that we showed that for two component system we can write it in an integrated form, which is a very compact form, which is basically you can write the mu A first, mu A, or we can actually start from the differential thing once again, mu A dNA plus mu B dNB, and then we integrated it to get it as mu A NA plus mu B NB. And remember that then you can actually start from this equation and again take a differential. So if I take the differential, I'll have, if I apply the chain rule, it will be d mu A NA plus, I have to take a differential with respect to NA, mu A dNA plus mu d mu B NA plus mu B dNB. But then you can easily see that these two terms appear here. So these two terms are nothing but dg itself. So it is nothing but dg plus, we can just rewrite it as Na du mu A plus Nb, this should be B, d mu B. So what we see that this term must be 0, or in general, if we write it as a summation for any arbitrary number of components, we see that sum over Ni d mu y should be 0. Now this equation is known as Gibbs-Duhem equation. Now what is the importance of this equation? Suppose we are dealing with two components, so we can write this d mu A, so this is 0, which means suppose if we write it, the d mu A in terms of d mu B, we'll have it is nothing but Nb by Na into d mu B. Now this is an interesting situation. What it tells is that if I want to change the partial, this is the chemical potential, if I want to change the chemical potential of one component, I cannot change it independently of the chemical potential of the other component because they are related. However, you could change the mole fraction. Remember, we changed the mole fraction of A, keeping all other mole fractions constant, Nb, Nc, whatever. So we said that we can change Ni, keeping all the Nj's constant where J is not equal to I. And then we can actually study how the Gibbs free energy or any thermodynamic quantity is changing. However, if we want to vary the chemical potential, we cannot, because the chemical potentials are coupled. So which means that the chemical potential for one component cannot change all by its own. So it has to change, all chemical potentials has to change, keeping a relationship between them. So they cannot change independently. So that is the essence of Gibbs-Duhem equation. Now suppose we want to measure or want to quantify the changes in Gibbs free energy for mixing for say some system, and to begin with, of course, we'll start with say ideal gas. Now since it is a mixing, we have to talk about two or more ideal gases, and suppose remember that if we take the Gibbs free energy of mixing, we have to keep the pressure and temperature also to be constant. So let us imagine that we have a container, something like say this, and initially I had Na moles of gas A or vapor A and Nb moles of gas B, and they were at same pressure and temperature, because once we mix it, if we assume that the pressure and temperature are changing, then we cannot apply it. So we have to use the full equation, which is dg is minus sdt plus pdv plus sum over mu I dni but we are now focusing only that part, which is sum over mu I dni. So in order to do that, the minus SDT term should be 0, and minus plus VDP term also has to be 0, which means pressure and temperature has to be kept constant. So the pressure and temperature does not change during mixing, and after mixing, what happens? We have Na here, and also we have Nb here. The total pressure should not change, and the temperature, of course, should not change. However, as you can see, the partial pressure of each component should change here, and that is the trick to figure out what is the change in the Gibbs free energy. Now let us just use this notation that, okay, fine, initially we had I could have written a GI, but I'm just not writing it because already we have chosen for to describe a component. So the initially the Gibbs free energy was nothing but Na mu A plus Nb mu B. So this is the Gibbs free energy of the joint system. Now when we mix it, but before we discuss that, let us also discuss, we already had this discussion, what is the Gibbs free energy, or the change of Gibbs free energy per mole when we change the pressure. So when we discuss the changes of Gibbs free energy as a function of pressure and temperature, remember that we got this kind of equation where we used an ideal gas as an example, and you can easily show that it will be RT PF by PI, because it is nothing but just the VDP term, and this V, now you are writing in terms of nRT by P, and if you just divide both sides by N, it will be RT by V, and this G will be nothing but Gm, the molar Gibbs free energy, and then if you integrate it, you will easily get this equation. So this is P final minus divided by P initial. Now so delta G is nothing but G final minus E initial. Now we are writing, suppose this final pressure as just P, and the initial pressure as P0. Now what is P0? P0 is nothing but the standard pressure, which by SI unit we are writing it as, say, 1 bar. We are keeping the 1 bar as a standard. So then this delta Gm is nothing but G final minus E initial, that we write as G minus the G initial corresponds to a standard condition where the pressure was kept to be 1 bar, that we write as Z0. Let us write this 0 as a superscript. So we get G minus Z0, and this is, remember, this is a molar quantity, so Gm minus Gm0 is nothing but RT ln P by P0. So in this case, actually the initial condition was actually 1 bar of the standard condition, or instead of G we could write it as in terms of mu, because molar Gibbs free energy is nothing but the chemical potential. So you can write that mu is mu0 plus RT ln P by P0. So that equation we are now going to use. So every mu here we could write it in terms of mu0 plus RT ln P by P0. So let us just write it. So I'll have Na mu A0 plus RT ln PA by P0. There is no point in writing PA0. P0 is same for everybody. It's just the standard condition, which is 1 bar. Some textbook actually drop this P0, and which means actually there is a inherent P0, and they just write it as ln P. But remember that this P is unitless. It has to be, because it's a logarithm of a number. So the idea is that it is expressed in units of bar, and then which means actually we are dividing it by 1 bar. And similarly for NB, component B, we can write mu B0 plus RT ln PB by P0. And now let us look at what happened to the final Gibbs free energy. The final Gibbs free energy, in our same notation, we could write it as, say, Na, and then suppose what is the change in the pressure. Now this pressure will be nothing but now the partial pressure, because now in the mixture the pressure contributed by A, or the component A, is nothing but the partial pressure. So instead of PA, we have to use some other quantity which we call as a partial pressure. Now remember, it's this PA, what is this PA? It was basically before mixing, but before mixing we took it to be pressure P. So instead of PA and PB, we could write it as P itself, and we'll denote the partial pressure as PA and PB, because the initial pressure, which is the pressure of A or pressure of B when the gases were not mixed, that was nothing but the P. It was because the pressure was kept same for A and B. But in the final case, we have the pressure of A is nothing but the partial pressure, and the pressure of B is the partial pressure of B. Of course, that should add up to P, because we did not change the total pressure from going from here to here. So the pressure and temperature were kept constant, which means the total pressure did not change. However, the partial pressure must have changed, because now it is a pressure of A in a mixture. So in that sense, we are writing it as mu A0 plus RT ln. Now we are writing PA by P0. Now this PA means now partial pressure, and the earlier P was the pressure for the total gas before mixing. So that was the initial condition. And similarly for NB, we can write NB into mu B0 plus RT ln PB by P0. So Pi is nothing but the partial pressure of component I, and of course it has to be in a mixture. So it is the pressure or partial pressure after mixing. So we can easily calculate what is the delta G of mixing, which is nothing but we have to take the difference between the final and the initial, and then you can easily calculate this quantity. You can see that we have a interesting relation here. So if you subtract G initial from G final, you can see that all these terms, mu A0, mu B0, they cancel, and finally we can get something like Na if we just collect the terms of Na together. So look at it. So we are subtracting this term from this term. So Na mu A0, Na mu A0 cancels. So all we are left with is Na times RT ln. Now I'll have RT ln P by P0 minus ln PA by P0, but that we can directly write as so this quantity, instead of writing it as a ln A minus ln B or ln X minus ln Y, we can write it directly as ln X by Y, and this P0 term will cancel. So we can write it as RT ln PA by P, and similarly for NB, we can also write it as RT ln PB by P. Now what is PB by P or PA by P? It is nothing but the mole fraction, because it is partial pressure by the total pressure, and that is equal to the mole fraction of XA. Similarly, this is nothing but the mole fraction of B, which we write as XA and XB. Now, this Na and Nb are nothing but the moles of A and B. That also we could write as a mole fraction into the total mole, which is nothing but, if we write it as XA into nRT, and here we can write it as XB into N into RT. So that nRT we can take common, and we can write XA ln XA plus XB ln XB. So this XA came from the definition that Xi is nothing but Ni divided by N. So we wrote instead of Ni, which is Na and Nb, as N into Xi, and then we took nRT common, and for this part we took the definition that the mole fraction is also defined as partial pressure divided by the total pressure. So either way you can write it, and you used the two definitions of mole fraction to arrive at this expression. So what we get in general, the delta G mixing, now instead of delta G mixing we could write it as delta mix of G, because that was our notation. Remember when we were talking about the transformation, we always wrote, like for example for a fusion process, how the enthalpy is changing, we are writing is delta fusion of H. In a similar way, we are also saying that we will write it as a change in the delta, or basically the process we will write as a subscript for the delta, and that quantity is nothing but in RT sum over Xi ln Xi, where Xi is the mole fraction of component I. Xi is nothing but mole fraction of component I. Now the mole fraction, remember, what is Xi? Xi can be minimum 0 and maximum 1. So Xi is a fraction, which means ln Xi, this quantity will be a negative quantity, which means delta G mixing is always negative for each component. So if we add up, it will be always negative together. So once we mix the things, keeping the, again, don't forget that we have to always write, this is done at a constant pressure and temperature. So when we mix two components together, the free energy or the total free energy actually changes, and it is negative, which means actually it is a spontaneous process. So if we want to plot how the delta G mixing looks like, if we vary, say, for two component system where I have Xa and Xb, suppose we are varying Xa, the minimum value of Xa can be 0 and the maximum value can be 1, and then the delta G for this minimum value should start from 0, because when A is 0, it means at this point Xb is 1. So it's a pure component, which is basically pure B. But then if I put here that Xa is 0 and Xb is 1, so for two component it will be nothing but nRT Xa ln Xa plus Xb ln Xb. So when Xa is 0, so this term is 0, and naturally Xb at this term is 1. Sorry, when Xa is 0, this is 0, and at that point ln Xb is 0. So the total thing is also 0. So delta G will start from 0 here. Similarly, when Xa is 1, this part is 0, and at that point xb is 0, so this term will be 0, so again delta g will be 0. So delta g will vary from 0 to 0, and in between it will have a minima. So the curve will look like qualitatively something like this. So it will have a minima for a particular composition of xa. Now the way I have drawn it, it looks very symmetrical. It may not be very symmetrical, meaning that we might hit an minima somewhere, say here, a particular mole fraction of xa, which automatically tells the mole fraction of xb, because always we are keeping xa plus xb to be equal to 1. So far what we have discussed is that we started our discussion on mixers. What happens if we have multiple components together, and then we showed that initially how the volume can be interpreted, or how the volume changes as we keep on adding one component, keeping all other components unchanged. And then we showed that it's not just simply additive, it keep on changes. And then we tried to define a quantity. We tried to see how the chemical potential, or Gibbs free energy per unit mole, that changes if we keep on changing the amount of one particular substance. And we showed that if we do it, then we get a definition of chemical potential, not only in terms of the amount of, not only in terms of the Gibbs free energy, but also in terms of any thermodynamic quantity like internal energy or enthalpy or Helmholtz free energy, which means actually the chemical potential is a very, very useful and very general concept. Now, when we are talking about chemical potential of a one component system, we wrote it as mu versus T, but in this case it's a partial chemical potential, or chemical potential of a substance. And then for that we used the relation for ideal gas, starting our discussion that how free energy or Gibbs free energy changes with respect to pressure. And then we can get a very interesting relation that mu is nothing but mu0 plus RTL and P by P0, only for ideal gas. And then you can use this to figure out if we had two different gases, and if we just mix it, starting with the initial condition that pressure, total pressure is nothing but the initial pressure of each gas. So then if we mix, the total pressure will not change. However, the partial pressure should change, and that fact we used, and we cleverly just wrote the mole fraction or the partial pressures in terms of mole fraction, as well as the moles of A and B in terms of mole fraction. And then we saw that the general equation for delta G mixing can be written as this. And we have argued also that this delta G will go through a minimum. It should be negative because it's a mole fraction. So all these xi's are fraction, and the reason for that is ln of a fraction is negative quantity. So delta G will go through a minimum. But how it will go through a minimum, it will depend on it will vary from one system to the other system. That we'll see.